All right, I'm going to do my best in this video to explain what is called the chi-square test of independence. Okay, this letter right here is a Greek letter. It's pronounced chi, and since we're squaring it, that's chi squared. And the way we write it out, I guess transliteration or whatever they call it, is chi square. Okay, and chi is pronounced like a k from a K and then a long I, so chi. All right, so this is called a chi-square test of independence. All right, so some variables or characteristics of the things that we research in, with statistics and in science, some of them are measured quantitatively. That means with numbers, okay? So, for example, the height of a person in inches or the weight of a mouse in grams, it's a number, right? And we call that a quantitative variable. Or the number of bedrooms in a house. All of these are we're counting something up. With a height, we're actually not counting something up. Maybe we're using like a tape measure or something. And with a mouse, we're probably maybe putting them on a scale and measuring in grams. But for bedrooms in a house, we just count 1, 2, 3 bedrooms or whatever. But because they result in numbers, we call them quantitative variables. But then some variables or characteristics in science are things that we research are measured based on what category they're in. We can't really apply a number to them. They're not quantitative. So for example, what if we were studying a student's major in college? If we surveyed 75 students and asked them, well, what's your major? Well, their major in college it's not a number, it's a word. And those words are compared to each other. We call them categories. So the variable is called a categorical variable. Or a person's nationality, what country they're from, or their race, or their religion. These are not numbers, they're categories, and so we call them categorical variables. Or the color that a house is painted, blue or gray or red or something like that. Okay, these are all what we call categorical variables. All right, now suppose we asked 80 college students about two categorical variables that affect them. So first we asked them, what is their preference in terms of when they take classes? Do they prefer early morning classes? Do they prefer midday classes? Do they prefer scheduling their classes in the afternoon? Do they like evening classes or weekend classes or maybe even online classes? Now that's six, that's 6 different categories, okay? Morning, midday, afternoon, evening, weekend, or online classes. And then let's say we ask whether they prefer to go to bed. What time do they like to go to bed in the night? Do they go to bed early in the night? Do they go to bed around midnight, or do they go to bed like after 1 in the morning? Are they a late night person and they go to bed at 1:30 or 2 or 3 o'clock in the morning? Okay, so that's now 3 categories. So here's what we could do. We could compare these 2 categorical variables, preference for when you want to take a class and when they prefer to go to bed at night. Okay, we could take those 2 categorical variables to see if they are related to each other or if they are independent. So if the 2 variables are related to each other, then they are not independent. But if they are independent, then they are not related to each other. So the only choices are either the 2 variables are related to each other or the 2 variables are independent. So related means that the category, whether they pick online class or early morning class or weekend class, the category that they pick on one variable has something to do with what they picked on the other variable, okay? And the way that works out is it could be that the people who prefer, morning classes are also the kind of people that might go to bed earlier in the evening. Now, I don't know that for sure, but it's a possibility, okay? And if that was true, then the two variables would be related. Dependent means that whatever the student picks on one of the categories has nothing to do with what they picked on the other variable. So whatever category they picked on the first variable doesn't affect in any way the category that they pick on the other variable. If that's true, then we say that the two variables are independent. And so the statistical test that we use to determine if the two categorical variables are independent of each other is called a chi-square test of independence, or chi-squared test of independence. Now, the way we go about conducting this chi-squared test of independence is we organize basically counts of which categories are picked by which subjects in a two-way contingency table. Two-way means that we have two variables. One of the variables is along the top, and one of the variables is along the side. Okay, so it's a two-way contingency table of the two variables, and it's broken up into categories. So this category right here, we would put however many students said that they prefer morning classes and they prefer going to bed early. So if let's say 17 students said that, then we would put a 17 right here, okay? And we would put how many students prefer evening classes and go to bed around midnight. We would put them here. And then down here, we would put all the students that prefer evening classes but go to bed after 1 in the morning. Okay, and ultimately, we would have numbers in all of these boxes. I call them cells, like in Excel, okay? So in all these cells, we'll have different numbers, and what will happen is we will add them up vertically and put a total right here. And we call that a column sum or a column total. So you can call this number here, the sum of this column can either be called a column total or a column sum. So this will be summed up here, summed up here, summed up here. This one will be summed up here. This one will be summed up here. And this one will be summed up here. Then we do the same thing horizontally. We sum up all these numbers and we put it right here. Then we sum up all these numbers and we put them right here. Then we add up all of the sums and put that number here. And whatever you see in the bottom corner here, that's our sample size. So the number that goes right here is going to have to be equal to your sample size, which in our example is 80, okay? And so first we organize all these counts into a contingency table, and then we do some interesting calculations to gather some statistics and be able to conclude whether the two variables are independent or related to each other. All right, here's the steps for conducting a chi-square test of independence. Step 1 is state the null and alternative hypotheses. Basically, we just do this one in words. The null hypothesis is that the two variables are independent. We assume that they're not related to each other. In fact, we assume that scientifically, we assume all variables are not related to each other until there is enough evidence to show that they are related to each other. So when it comes to trying to relate two variables to each other, we don't assume that variables are related to each other. We assume that they are independent of each other. Then our alternative hypothesis is that the two variables are not independent of each other, which means that they are related to each other. So we would have to reject the null hypothesis. We would have to reject it in order to conclude that the two variables are related to each other. Now, as a note, know that this is a right tail test. It is always a right tail test. Why? Well, because it actually uses what's called the chi-square distribution. It doesn't use the t-distribution or the normal distribution. It uses a new distribution that we're going to look at called the chi-square distribution. And the chi-square distribution starts at the origin and then it has sort of a weird shape, but sometimes it looks like this and sometimes it looks like this, but it always winds up stretching out to the right. And so we're always testing over on the right tail. There is no left tail because it always starts at 0. So there is no left tail in the chi-square distribution. All right, in step 2, we're going to do 3 things. 1, we're going to identify the level of significance, which is the alpha, just like in other significance tests. We're going to state the p-value rejection rule, and here's what it looks like. We're going to reject H sub O if our p-value is less than whatever the value of our alpha is. Okay? So if alpha is 0.01, we would say reject H sub O if p is less than 0.01. Okay? Last thing, we're going to calculate the degrees of freedom. Now, the degrees of freedom are an interesting thing in a chi-square test of independence. What we have to do is we take the number of rows, which is basically the number of categories in one of the variables, and we subtract 1 from that number. Then we take the number of columns, which is the number of categories in the other variable, and we subtract 1 from that number also. Then we take those two numbers and we multiply them together, and that gives us our degrees of freedom. All right, in step 3, we're going to complete what's the contingency table of observed values that I showed you an example of before. Okay, now you may want to pause this and write out this whole step. This is a very important step. We're going to complete a contingency table of observed values. What are observed values? Well, it's what the sample, the people that we sampled or the things that we sampled, it's the actual counts that we observed in our survey. Okay, so we're going to make a contingency table and we're going to put in the counts of our observed values from the sample across the two variables. And we're going to do an example in just a minute of this, okay? Then what we're going to do is, after we've completed the contingency table, we're actually going to complete a similar contingency table, a second one of what are called the expected values of the crossovers of the two categories. Now, the contingency table for the expected values is going to have the same column sums and the same row sums as the observed values contingency table. It's also going to have the same n, the same sample size. And now write this formula down. This is the formula for calculating all the expected values that are going to go in all the cells in the second contingency table. For each individual cell, you're going to multiply the column sum of that cell times the row sum of that cell. Then you're going to divide that product by the sample size, n. And whatever number you get from that, you're going to put in that box for that cell. So why don't we do an example of step 3? Let's go ahead and try an example. All right, so here's a small contingency table. Look, we have two categories on one variable. Let's say we're asking some people, I don't know, high schoolers, maybe college students, whether they're an athlete or not an athlete, and whether they are male or female, okay? And so we only have 4 boxes, 4 cells. We have this box is all the people who answered that they are male and that they are an athlete. These are all the people who answered that they are female and that they are an athlete. And then these are the people who answered that they are male but not an athlete. And then these are the people who answered that they are female and not an athlete, okay? So the first thing we're going to do is we're going to total this column. We're going to call this the athlete column, okay? This is the athlete column. And 34 plus 23 is 57. So this is our column total. Then the column for not an athlete, we're going to sum that up. 31 plus 19, that's 50. So we'll put 50 here. And now we can actually sum it up sideways. 57 plus 50, that's 107. And so it looks like our n is 107. Our sample size is 107. Now we're going to do our row totals. We're going to add up these two numbers. 34 plus 31 is 65. We're going to put that right here. Then we're going to do this row total, and we're going to put it here. 23 plus 19 is 42. And you'll see that if we add up 65 plus 42, once again, we get 107. Now we're going to transfer the column totals over to our expected values contingency table. So we're going to bring 57 right over here. We're going to put it in just the same place, 57. Then we're going to take 50, and we're going to put it right here in just the same place, 50. We're also going to bring over the sample size, 107. We're going to put it in just the same place, 107. Now we're going to bring over the row totals, 65. We're going to bring that over here, 65. And then 42, we're going to bring that over and put it right here, 42. Okay, there we go. And now, to get this number and this number and this number and this number, we're going to use that formula that I showed you before. Let me go get that formula. All right, so here's our formula. We're going to multiply the column sum. So for this one right here, the number, the expected value that we're going to put right here, we're going to multiply the column sum, that's 57. So 57 times the row sum. So it's this one. So this is the column sum, and this is the row sum. So we're going to do 57 times 65, and that's going to put us right there. So 57 times 65. And then we're going to divide by the sample size, which is 107. So we're going to do 57 times 65 divided by 107. So let's go over to a calculator here, and we're going to do 57 times 65 divided by 107. And here's what we get. We get 34.626. Now we could try and put 626.16822, but there's not a lot of room in that box. So let's just do 34.626. So 34.626. Now it's important to understand that in the observed contingency table, we're going to have whole numbers. These are counts. We're counting research objects like people or houses or cars, okay? But expected values, kind of like an average or a mean, they don't have to be whole numbers. They can be decimal values, okay? Now here's the cool thing. Because we already have one of the counts, I know that this box plus this box has to equal 57. So what I could do is I could just do 57 minus 34.626. So I'm going to do 57 minus 34.626, and I can put a few more decimals on it here if I want to, 168 maybe. And I get 22.373. This 8 is going to turn this 3 into a 4. So we're going to have 22.374. So 22.374, okay? And now we could over here, we could just do 65 minus 34.626. But I actually want to do the calculation here so that you can see the example. So for here, we're going to do the column total, 50, times the row total, 65. So 50 times 65. All right, so 50 times 65 divided by the sample size, 107. All right, so it's 50 times 65 divided by 107. And that's going to give us 30.374. This 8 is going to turn this 3 into a 4. So 30.374. So it's 30.374. And now to get this number here, we could just do 50 minus 30.374. But I want to show you the calculation. So I am going to do 50 times 42. So for this one right here, the row total is here. And for this one right here, for this one, the column total is here. And for here, the row total is over here. So we're going to do 50 times 42. In fact, I can make it really easy here if I just get rid of this 65. I can now just do 50 times 42 divided by 107. So 50 times 42 divided by 107. And that's going to give us 19.626. 19.626. And you can see that 19 plus 30 is 49. And then 0.374 plus 0.626 is 1. And so if you add these together, you get 50. And the same thing will happen this direction. You'll have 42. Okay? All right, so that is how we create an expected values table given an observed values table. That was step 3 of the chi-square test of independence. In step 4, we're going to identify the critical value for chi-square. Okay, and you can do that either in the NumWorks calculator, you can do it in Minitab, you can use a paper table or digital table. There's all kinds of places where you can get the critical value. But just like finding the critical value for a t-test or for a z-test, it's going to be based on the alpha or the p-value. And in this case, we have degrees of freedom, so it's going to be based on the degrees of freedom as well. So we take the alpha and the degrees of freedom, and we go into either a table or into our statistical software to find the chi-squared distribution and find out what cutoff critical value gives us that particular alpha or p-value. Okay. Then once you've identified the critical value, you can then state the test statistic decision rule, which you've seen before. It's just like the test statistic decision rule for a z-test or for a t-test. We're going to reject H sub O, the null hypothesis. We're going to reject it if the chi-square statistic is greater than the critical chi-square value. Now let me show you where we're going to go in the NumWorks calculator to find this chi-square distribution. All right, in the NumWorks calculator, we're going to go down to distributions. We're going to hit OK. Then you can see down here, chi-squared. This is our distribution, the chi-squared distribution. So we're going to select that one. And you can see that it asks for a degrees of freedom. And so depending on how you calculate, when you calculate your degrees of freedom, how many columns, how many rows you have, let's say the degrees of freedom in this case is, 3. So we go to 3, then we go down to next. And look, you can see that the chi-square distribution starts at 0. There is no left tail. There's only a tail on the right-hand side. Now, it does allow you to do a, let me move this over. It does allow you to do a left shading. That doesn't necessarily mean there's a left tail. It just means that you're going to be shading the left side of the distribution. But we want to do a right tail test pretty much every time. So we're going to come down here to the one where it shows the right side shaded. Then you would come over here and you would put in some sort of alpha. Like what if we put in 0.05? And then our critical chi-score would be 7.814728. And that's how you would get the critical value for the chi-square. All right, step 5 is a big one. This is where we calculate the chi-square test statistic that we're going to compare against the critical chi-square value. Okay, so to calculate the chi-square test statistic, here is your formula. Go ahead and write this formula down. You're going to want to pause and write this down. Chi-squared equals, now this is a Greek letter sigma. This means that we're going to add up a bunch of stuff. We're going to sum up. We're going to sum up a whole bunch of things. That's whenever you see this sigma, that's what that means. Well, how many things are we going to sum up? We're going to sum up however many, whatever our number of cells is, okay? So really, it's going to be however many boxes there were, okay? Let's go back to that example that we looked at. All right, so in this particular example, we had to calculate 1, 2, 3, 4 expected values. And so for the chi-square test statistic, we would be adding up 1 plus 2 plus 3 plus 4 things. the number of things you're going to add up is going to be equal to the number of these boxes where you had to calculate an expected value. So what are you going to add up? Okay, let's say you're adding up 4 of them. What are you adding up? Well, here's what you have to do. For every single one of them, you have to take the observed value from the observed contingency table, subtract the expected value from the expected contingency table, then take that difference and square it. Then divide that number by the expected value. This will now give you one number, which is often called the contribution, and you would then add up all 4 of them, or 6 of them, or 9 of them, or however many of them that you get. All right, and then the last step, step 6, you're going to identify the p-value that goes with the chi-square test statistic from step 5. Well, where are you going to plug it in? Well, you're going to take that test statistic from step 5 and you're going to go into the chi-square distribution, either in NumWorks or in Minitab or somewhere, and then it's going to give you a p-value that goes with that chi-squared test statistic. Then once you have that p-value, you can make a decision. What do you mean make a decision? You know what I mean. You're either going to say reject H sub O, and if you reject H sub O, that means that the 2 variables are not independent. And so this means the 2 variables are not independent. That means they're related to each other, okay? Or it means that you have statistical evidence to suggest they're related to each other. And if you do not reject H sub O, then you do not reject H sub O. So those are the only 2 choices. That's what I mean by make a decision. And if you do not reject H sub O, then that means that the evidence suggests that the 2 variables are independent of each other, that they're not related to each other, okay? All right, so this is the whole procedure for chi-squared test of independence, and hopefully you wrote down all the steps. And what we're going to do in the next video is we're going to do an example, and then maybe we'll even do a 3rd video with even more examples.